Okay, we're doing problem number 17. And in 17, we are designing this 1,000 cubic centimeter right cylindrical can. So think of that as like a soda can, something like that, just a right cylindrical can. And the book talks about the manufacture of this can is going to take waste into account, meaning for the top and the bottom, they're actually pressing those out of squares, and then to get the circle, your top and bottom, and then the other part of that they're just kind of throwing away. And so the book explains a little bit how they come up with this area equation. So the amount of material, so there's the top and the bottom. It was 4r squared, and 4r squared gave it 8r squared. And the side is 2 pi rh. For us, we're just going to kind of take that formula, and we want the ratio of h to r. And what are we doing here? Oh, and it doesn't say in this. I kind of paraphrase the question. We're obviously going to minimize. I guess that's obvious. We're going to minimize the amount of material used. So we begin right here with our A equation. A equals 8r squared plus 2 pi r h. We want to minimize that. So you're ready to take a derivative, except for the fact you have two variables in here. So you come up here, you look for any other information that you have, and it tells us it's 1,000 cubic centimeter right cylindrical can. And so you go to the volume of a cylinder, is pi r squared h. We know our volume is 1,000, so you get 1,000 equals pi r squared h. So now, let's look over here. What would you like to solve for? Do you want to solve for r? Do you want to solve for h? I guess I'm kind of leaning for h because I only have to sub in once. So if I come back here to the right, 1,000 over pi r squared equals h. So we come back to our area equation. Area is 8r squared, 2 pi r, and I've got 1,000 over pi r squared. We can simplify that just a little bit. The pi's cancel out. One of the r's cancels out. And if we simplify this, we get our area equals 8r squared plus, it looks like 2,000 over r. What's our domain? Well, let's see. R certainly has to be positive. And what's the biggest the radius could be? Well, we're kind of bound by the fact that it's 1,000 cubic centimeters over here. But really, r could be as big as you want because you can make it incredibly tiny, the height, to come up with that 1,000. So r is going to be positive. That's about the best we can say with our domain. All right, let's take the derivative. 8r squared becomes 16r. We have here r to the negative 1, so I get minus 2,000 over r squared. Immediately I see critical point. It's when r equals 0, but that's not in our domain because r is going to be positive. So I'll set this equal to 0, and look where my derivative is 0 here. All right, so I've got 16r is 2,000 over r squared. I cross multiply. It looks like 16r cubed is 2,000. I'll divide this by 16. And 16 goes into 2,000, goes into 20 once, into 40 twice, and into 85 times. So r, ooh, that came out very nice, didn't it? So r cubed is 125. I'll take the cube root, and look how nice that is. R equals 5. I wonder if that's truly a max or a min. Well, it's my only critical point in the domain, because when r is positive, that's my only critical point. So let's take a look at a quick little chart. Here's x, here's a prime. My only critical point is 5. I'll go from 0 to 5. I'll go from 5 on to infinity. I'll choose some value between 0 and 5. How about 1? I'll sub a 1 into my derivative. And let's see, I get 16. I get 2,000 divided by 1. 16 minus 2,000 is negative. All right, how about bigger? From 5 to a million. I'm sorry, 5 to infinity. How about if I go with 1,000,000? Well, I've sub in here for r. I'll put in 1,000,000. I have 2,000 divided by 1,000,000 squared. That's not much. 16 times a million is a lot. That will certainly be positive. So my derivative switches from negative to positive. So r equals 5, my critical point is going to be a min, because a prime switches from negative, that's a negative there, negative to positive. And that's my only critical point on the domain, and so that is my min. Now, let's answer the question, because the question was some kind of a ratio of h to r or r to h. So we come back up here, the ratio of h to r. Well, let's find h. H is over here, so it's 1,000 over pi. We just found r. R was 5. 5 squared is 25. And let's see, 25 goes into 1,000 40 times. So 40 over pi equals h. And then the final answer here, they want the ratio of h to r. So this ratio of h to r, I have 40 over pi compared to 5. Reduce that by 5. And it looks like the ratio, reduce it by 5, is 8 to pi. Pi we know is 3.14. So the height is about 2.5 times bigger than the radius. That would be the ratio, and that's the radius we're talking about, not the diameter. So the height is 2.5 times bigger than the radius if you're going to minimize the amount of material used. That completes this problem.